Hey folks, can you hear me all right? Love the enthusiasm in the chat. Where's everybody from? All right, all over the place. Nobody from Oklahoma, which is, the part of the US that I'm from. Just gonna wait 1 or 2 more minutes before we get started. Antarctica, wow. I bet your GPUs stay cold. Is anybody training their own model today? Just curious. Nice. Awesome. Did anybody think about training a model but then decide it's too hard or something? Too expensive. That's fair. Don't worry, Toby. I'll explain what that means soon. Okay, I think it's about time to get started. So, I don't have quite the right brain type to present while the Q&A is going, so I'm going to basically talk for about 20 minutes, including giving a little demo, and then I'll sort of change my focus to the Q&A. We can have some discussion. Yeah, so thanks for coming out. My name is Ben Cowan. I'm a forward deployed machine learning engineer at Modal. And today I wanted to talk about some interesting trends we're seeing among our customers, specifically related to fine-tuning or training your own model. And so I'm going to talk about some reasons that people choose to train their model and some reasons people choose not to train their model. But what I would love for you to walk away from this webinar with is some confidence that one, you have what you need to decide when it's time to train. It's not, you don't need to hire a research team just to train a model these days. And yeah, hopefully you're interested in using Modal to do it. So without further ado, first, in case you're not familiar, wanted to give a little bit of context to this, the perspective I have on this. So Modal is a general purpose compute platform. We built our own container runtime. We have our own orchestration engine, and it's all designed to get us basically fast developer iteration. So we want to be able to try stuff and iterate on mistakes and making things better and better as fast as possible. So What we did is we built some basic building blocks that sort of compute building blocks, if you will, that allow our users to build all kinds of stuff. So we have functions that sort of auto scale the amount of compute you have to track, like, basically how much traffic you have second to second. We have sandboxes, which are secure containers that are safe to run, for example, LLM generated code in them. And we have other sort of cloud primitives that you'd expect any cloud provider to have, like distributed storage, networking, etc. So, as a forward deployed engineer at Modal, my job is to basically help machine learning scientists and engineers build stuff with these building blocks. And I've had the pleasure of kind of working on maybe all corners of the machine learning landscape, from weather forecasting to protein folding to LLMs and agents. And one way that I've started to categorize my customers is in terms of this thing I'm calling the model spectrum. The hot take version of this is the AI maturity curve, but I like to call it the model spectrum. And it kind of ranges from doing everything completely from scratch by yourself to using frontier APIs. And so I'm going to start there because that is, the most common way to get started these days with AI, right? So you sign up for an API subscription, and then you can pretty much build anything. They have this framework has ushered in kind of a new era of startups and business in general, because the barrier to entry for building is so much lower. So why did they have that such a huge effect, on business? I think it's because, one, of the fast iteration time. You can, build stuff at the speed of, an LLM inference, and then their general purpose. So you can pivot on a moment's notice, add new features, change directions for your customer. Maybe a big new customer comes in and they didn't quite understand your product. Well, you can just change your product much faster. And it is truly, abstracted or even removed any thought about infrastructure. I've met people who have no idea that their prompts are being processed on a GPU when they use, Chat GPT or something. You don't need to know any of that, even to build a business around it. But when you build a business around this type of product, there's some bottlenecks that you're sort of bound to run into eventually, in my opinion. You can kind of like categorize them into like bottlenecks around the deployment versus bottlenecks around the model performance, itself. And so on the deployment side, let's say you have a new customer and they require, 50 millisecond latency. There's really nothing you can do to optimize the, your API endpoint that you're hitting. And the same would be true for throughput or even some custom metric. Because it's so abstracted away, you don't have any control. The other thing that's tough to scale is the cost. So when you have more and more employees, the economics of, paying for tokens, it really starts to add up, the costs. But the one I really wanted to focus on today is the model differentiation, right? So if your business is built around a frontier models API, then your moat is the harness, right? It's the framework you've built around the API because the model itself is the same model that other people are using. And so, yeah, a big what I'm trying to say is that a big reason we see people choosing to train their model is not just optimizing these bottlenecks, but to create more differentiation. So in principle, if you train your model, on your customer data and interactions, the actual weights of the model will have, experience or information about your, product service that no one else is going to have, even if they somehow had the exact same harness. One interesting point that has come up when I've given this talk before is that there are training APIs that these labs offer. So basically, you give them your data and they train their own model for you. And so basically, what happens is the model behind the endpoint changes, it updates, and it is differentiated because it's incorporated your data. The main drawback of this is that you have no control whatsoever over the training algorithm. So if you did want to tune it, if it wasn't quite what you were looking for, you don't have the control over that. And one of the things I'm going to be talking about today is that tuning these training algorithms, it's much more of a craft and a engineering task than it used to be. It's not a research task. It doesn't have to be anymore. So we'll get into that soon. But first, I wanted to mention, so traditionally, if you were not training a model and then you decided, okay, we're going to train and deploy our trained model, that is a huge jump sort of to the other end of the spectrum traditionally, like 10 years ago. Not only do you need people who can implement the training algorithm, but you need people who can manage this sort of new workload, because training has very different compute or scaling characteristics than a typical production app. So training can run for a long time, utilizing many GPUs at the same time. So it raises your baseline usage significantly. And then in between training runs, it leaves a big gap. And this isn't tied to traffic or time of day necessarily. And so this kind of, if you are managing your own infrastructure with something like Kubernetes, this kind of basically introduces a whole other problem of managing resources, trying not to underutilize what you have, and so forth. And so Modal's ethos is that every single company in the world shouldn't have to solve this exact same problem, right? You shouldn't have to have a cloud engineering team in every company all sort of doing the same stuff. So I'm going to talk about how we address this. I will say, like, the pro of this, though, of training your own models, you have complete control. So if basically you can tune your training algorithm, you can define the reward functions or loss functions very specifically. And this is typically going to get you a better model. So we've talked about kind of the two ends of the spectrum. And now I want to sort of justify this claim that there's a strong demand for this. This is a sort of viral tweet where several sort of AI thought leaders are called out for having publicly shared, getting amazing gains from training their own model. Not only to improve performance on a task, but it's generally cheaper because you can optimize the deployment for cost. And so there's this term called domain specific that comes up. And if you search this term in iClear or NeurIPS or other machine learning conference proceedings, it comes up quite a bit. And there's sort of a well accepted concept that domain specific models can beat general purpose models, on domain specific tasks. Okay. And so this is kind of like saying, a surgeon is going to do better surgery than the smartest person in the world who's never done surgery. And I think that's, fairly easy to accept. One of our customers, Decagon, put this very succinctly, that basically saying that the major labs have different priorities than their product, and I think that's pretty normal, right? So most startups and companies that are becoming more and more specialized, the word specialized itself kind of is related to being domain specific, right? So there's kind of a line in the sand, and there's a question that business owners, machine learning engineers should be thinking about. Where am I? Like, am I crossed the line into domain specific? Am I going to be in a year? And so I want to talk about some signals that could potentially signal where you are. And yeah, I guess actually before that, you probably never saw this coming, but I'm going to say there's a great happy middle ground now, with modern compute providers like Modal and modern open source libraries like Hugging Face's TRL library. You can kind of get the best of all worlds here, where you have control of the algorithm, so you can train a domain specific model without having to build everything from scratch and hire a research team. And best of all, this approach lets you retain that fast iteration that lets you quickly pivot when needed. Okay, so this is sort of my hottest take summarization of what I'm trying to say. It's just a matter of time until your product becomes domain specific. Obviously, this doesn't apply to every product ever, but sort of by definition, if you're differentiating, if you're becoming the very best at the service you provide, you're getting more specific. And so if you're kind of on that path, what are some signals that could indicate that you're ready to train? So kind of relating back to what I was talking about earlier, if any of those bottlenecks are pain points for you, that is a signal. So if you're paying more for API tokens than your business is making, that could be a sign that you would benefit from an optimized deployment. If you are turning down contracts because you aren't able to optimize for latency or throughput, that is a pretty strong signal that you would benefit from a custom deployment. And this is the big one here, if your evals are plateauing. I always have to acknowledge caveman mode when we talk about optimizing without training. So you can use something like, you basically tell your model to speak in caveman mode, and it reduces token usage by a lot. But you can only do that once. You can't use caveman mode on an already caveman moded model or prompt. So anyway, let's say you go to caveman mode and you are still, paying too much and your evals are not improving. Your product isn't getting better. That could be a sign that it's time to train. Um, some really important signals that you should not try to train your own model would be if you're still, defining your product. So if your core functionality is not defined, and you might need to pivot wildly for the next customer tomorrow, it's probably too early to train. If you haven't been collecting any data on your customer interactions, on your performance, your evals, then you're probably not ready to train today because you need data. Um, and that's what segues into this next part of the slide, which is what do you need to get started? If you're interested in training, or you think you might want to train in a year, what can you do now to prepare? And I think the good news is that there's a good chance that you've already done the hardest part, which is building your agent harness and eval suite. So if you're evaluating your product and your model, and your model framework, that is, and tracing customer interactions and decisions, and whether they were good or bad decisions, then you have data that could be used for training. Might need a little curation, but yeah, I think that does kind of come naturally for a lot of companies. But if you're not doing it yet, I would get started now, because it's only a matter of time till you're gonna have to think, well, what if I did train? Um, yeah, so that was the main sort of lecture part of the presentation. So thanks for bearing with me. And now I would like to show you a little demo. And so this is the GRPO algorithm. So it's group relative policy optimization. It's a reinforcement learning algorithm implemented with Hugging Face's TRL library, which is Transformers Reinforcement library. And this is just 300 lines of code. It's on Modal. You can go search GRPO at modal.com/docs, or you can type this URL in to see the rendered version. At that link, there's also the GitHub commands, the git commands to clone the repo and find this example in our public repository. It's just 300 lines of code, and it uses the TRL library to train a coding agent. So before I switch over to my IDE and execute this, I wanted to just give a bigger picture idea of the pattern that's implemented here, and why this is so easy. The punchline is that because Modal provides these auto-scaling functions and sandbox APIs that kind of unify the building blocks you need to create this type of pattern. So what I'm going to show you is sort of the base function. It's a Modal function that fires off a GRPO trainer instance. And so this is the core training loop that's implemented by Hugging Face, and it uses a GPU. It can be enhanced by running a vLLM server. And now what's really cool about this library is that you can give it a reward hook, right? So you can basically say, okay, this is the function you should evaluate to determine how good the model's doing. And you can give this library a modal function that auto scales. And so that's exactly what we've done. We have this other modal function called compute reward, which takes the model's code because it's a coding model. So we're asking it to write code and then evaluating it against some tests in a sandbox, which is a secure execution environment. All right, let's go look at the code. This. All right. So here is my IDE. And the first thing I'm going to do, I'm going to go ahead and kick this off. So this is the file in the Modal examples repo. You can download this for free. And it has the commands that you need to run it right up here. So I'm just going to type in Modal run and then copy the path to this file. Kick that off, and then I'll just talk through this file a little bit while that's running. One thing to note is to run this, you need a Modal account, so you need a Modal API key. And you need a weights and biases API key. So this is just sort of a visualization library that we're using. I'll show you what it looks like in a minute, but you can make a free account. And then the only changes I made to this file is that I told it to, keep going and going, so we actually get a plot. And I asked it to log, very frequently. Right. So when this command I executed, the Modal run, it's basically creating an ephemeral app that looks at this file and then finds this function, train. So I'm going to search def train. And so you can see this is just a very thin modal wrapper. So it's just calling this other function. But the reason we wrapped it in this this decorator is to tell Modal, hey, whenever you run this, it needs to have an H100. Okay, so just a few lines of code to give this container a GPU, this function. And we have a couple different versions. So this one down here shows how to run it with vLLM, a vLLM server running on one GPU, the optimizer on another GPU. But we can just keep it simple for now. So let's find this function, start GRPO trainer. And yeah, if you did your, grad school 10 years ago, like me, there's a pretty good chance that you, even if you did machine learning, that you never worked on reinforcement learning. So it can seem maybe foreign if you're not used to thinking about it, but it's encapsulated in these really nice libraries. So this GRPO trainer is something we've imported from TRL. And all we have to do is give it a few arguments to kick it off. So we're telling it to take this open source Quen model as the base model to train. We are, defining some training arguments, basically saying, okay, output stuff goes here, use weights and biases, train for this many steps, etc. We're telling it to use this data set. Okay, now this is probably the hardest part to do, on your own. So you need to curate a data set. But you can use these open source ones to as a template, right, to kind of guide how to curate your data set. So in this case, we're training a coding agent. So we're using this open coder data set, which is basically, it has a few things. It has the instructions and the prompts to basically, prompt the model. So telling it, okay, write a program that does X, Y, Z. And then it also has test cases. So we're going to judge the model on whether it passes these tests. I'll show you exactly how we implemented that. So the trainer takes the model, the args, the data set, and then this is the really cool part, the reward helper function. So this takes a list of completion. So this is the model's predicted or generated code and corresponding test cases. And then we are just passing this to another modal function and saying, okay, take all these pairs and fan out, do it all at once. That's what starmap is doing. So let's go see what this is doing here. It's just a few more lines of code where we're firing up a modal sandbox and pre-processing the generated code a little bit. I'll show you that in a second. And then we're running Python code, right? So we're just executing the code, and if it completes without any failure codes, then we give it a positive score. Otherwise, it gets 0 as a score. So let's just take a quick look at this. So we're all on the same page. So this is just a little bit of a logistical thing where we're basically taking the model's generated text and we're finding the actual Python code within that completion, doing a little formatting, and then we're appending the test case. So this is from the data set. And then we're just sort of appending it all together with a little formatting. And so that is all ready to just run, execute with Python. If it fails, then it'll have a non-zero return code, and we'll give it a 0 score. Yeah, so this is how it works. And one thing I wanted to mention is that a common thing people use Modal for is GPU sandboxes. So let's say you want to train the model to write CUDA, write kernels, or write efficient GPU code in general. Modal sandboxes can take this same simplistic GPU argument, and then they'll all have a GPU. Okay, so this has been running for a bit. Let's go see what's been happening. Just scrolling back up, because weights and biases prints out this nice link. So view run at this link. So let's follow that, see where it takes us. And yeah, it has a bunch of nice little plots. So this is basic. It's a similar experience to TensorBoard, if you're used to that. But it's showing the profiles of the trainer, and then it's showing the reward. So we have a reward of 1 if it succeeds, or 0 otherwise. So you can see that it does succeed now and again. And so if you run this for a really long time, it'll hopefully get better and better. All right, I'm going to go back to my slides now. Sorry if you can hear the sirens. I live in New York, kind of near a hospital. So, okay, so coming back to the bigger picture, this is the pattern that I just walked through. And yeah, it's just a nice unified set of APIs. Oh yeah, so basically the last thing I wanted to mention is that this whole file is 300 lines of code. And in it is this little snippet that deploys the trained weights in vLLM. And so this is, an inference API that you can query after training. Yeah, so I think that's it for the presentation. I'm going to open the Q&A tab and look at some of this stuff. How does vLLM help? Yeah, that's a good question. So vLLM is an inference engine, and so basically, when you give it weights of a model, it does some sort of I'm trying to think of the right way to say this, some inline optimizations. So sort of right there on the device, it sort of analyzes the model, and it's called compiling, just-in-time compiling. And the long and short of it is that you can get like higher, tokens per second. So it creates a more efficient version of the model than, for example, just running it with plain Python. In the context of training, it makes the inference part faster. And so inference is used very heavily in this GRPO algorithm because it is generating all these um, code snippets. So, for example, you could imagine it's not just writing a little program, but it's generating edits to a large repository or something. So it's doing a lot of inferencing um, for um, each iteration. Hmm. How do concepts like model and data parallelism works? Yeah, so um, modal, that's a great question. And there's a couple different aspects to it. So as you saw in the code, to get a GPU container, it's just a string of the GPU you want. So H100, for example. If you want more than one GPU in the container, it's just :8. So H100 :8, for example. And so if you request a container with multiple GPUs in it, you can use, data and model parallelism type tools within the container as usual. So Modal doesn't have like a primitive for this because you can use the regular ones. We also have a multi-node product. So if you need more than 8 GPUs, it's possible, but that's currently in private beta. What all is required in the data sets for a specific domain? For a telecom domain, I might need a little bit more context on the telecom aspect, but it really comes down to designing a reward function. If we're talking about reinforcement learning here, one thing that I kind of glossed over earlier is that typically, if you're training a model, like the first thing you would try is supervised fine tuning, which is much simpler. And in that case, you basically, as with any supervised learning, you need example inputs with example outputs. And then there's sort of a whole host of different, basically ways to compare like a prediction and the actual output to train the model on how good it's doing. So for supervised learning, you need input and output examples. For something like behavioral training with reinforcement learning, actually the example I showed is a little bit of a not pathological, but it's a little bit of a simplified example, right? So we were basically giving no feedback whatsoever except yes, you passed the tests, or no, you didn't. So that's, in technical terms, that would be called a sparse reward because, you just get zeros a lot of the time. which is not actually that very useful information. Okay, so if you were going to start collecting data um, with that in mind, it's like my main recommendation is to collect as rich of a trace as possible. So, what decisions did the agent make along the way, including the final recommendation? You could even, track in terms of like how much did it cost to create that recommendation, and then you also need follow-ups. So if it made if it was like a customer interaction, was the customer satisfied? Did they come back? Like maybe it looked good, but didn't actually work. All of that kind of stuff. So the more, the better. What do I mean by the agent harness in order to get started? Um, Yeah, so when I'm talking about an agent harness, I'm kind of specifically um, talking about a certain type of product. So if you are using an agent, right? So if your AI is performing tasks as part of your service or product, um, that the harness is the means by which the AI, the model can sort of interact with the world. So that could be tool calls, referencing some other context like RAG or some kind of database. That's the harness. It's sort of the interface between the agent and your systems, and the way that its outputs are provided to the customer. Um, how to run this in a local system. Um, yeah, so if you have GPUs, then you could pretty easily modify that example to run locally. Um, but like basically what's not easy to port would be the parallelism. So we used modal functions and to sort of fan out containers, and modal sandboxes to safely execute the generated code. So yeah, to be a little more clear, modals compute building blocks that I've been talking about, those cannot run on your local machine. It's kind of inherently tied to our cloud substrate, our cloud machines. So yeah, so to run it in a local system, like the TRL library is open source, so you could run it. It's just that the parallelization of the reward function is that's pretty important for scaling this up for something like training a big LLM. All right. When we fine tune the model, does it overfit against the pairs? Or if a query is somewhat related, will it recognize the pattern? Alternatively, does fine-tuning involve augmenting the queries in all possible ways? So the short answer is yes, that overfitting is still a danger in reinforcement learning as it is in supervised learning. So if you're not familiar, overfitting basically means that your model is memorizing the data instead of learning to understand the general concepts that you tried to represent by the data. So if you fit too closely and memorize stuff, you might you know accidentally memorize noise or memorize an outlier, instead of learning like a more general concept that will apply to more broad situations. And so, yes, this overfitting is a word is something you have to be careful of um, in supervised or reinforcement learning. Okay, so then the follow-up question is um, about augmentation, data augmentation. And yeah, I mean, sorry, it's kind of a boring answer, but yes, you should augment your data if you have uh, a good idea of what a sensible augmentation is. And so let me define that for everybody as well. So data augmentation is basically the idea where, okay, you have your training data sets and it represents your problem to some extent, but you know that it doesn't represent some similar situation. So you can tweak your data to kind of artificially uh, expand your data set. Okay. That's called data augmentation. So you're augmenting the data set generally with prior knowledge about what ought to be learned by the model. And so, yes, you should augment your data if it's relevant, right? So if you know that uh, there's something not represented that should be, then yeah, I would recommend that you do it. Um, is there a way you can contribute to modal sandbox internals? So sandbox internals are not in an open repository. So no, you can't make PRs to the sandbox product directly. The most valuable thing you can do to contribute is to provide repros or reproductions of the issue um, in a sort of minimal, simplified format. So that makes it really easy for people like me, the forward deployed engineer, to understand the problem and characterize it. Yeah. I think I already did this one. Okay, I'm scrolling back up. Yeah, this is a great question. So, can we train a very simple vision model? So let's say you have a set of images, like screenshots for a specific application. Can you train a model to be better than, say, a regular OCR model? So this actually this is a great question, and it kind of ties into the overfitting question, right? So there's sort of a philosophical question um, where if we're stepping back a bit and talking about that term I mentioned of domain-specific models, from the perspective of a foundation lab, you could say, well, those models are overfit to that problem. They're not either, like they're missing the broader intelligence for that specific problem. And so in the same manner, kind of zooming in here, um, you're basically asking, can I train a model like on a specific application screenshots? And you certainly could, but the hard part would be to do it in a way that isn't overfitting to like screenshots specifically is I guess I'm kind of picturing it as a fairly like manual process that could be maybe prone to overfitting unless you have sort of a way of doing like a huge number of screenshots in a lot of different situations to create a nice broad data set. Um, but assuming that you have, done that and you have a broad data set, um, then you might be able to get better performance. But let me actually temper my answer with the last few words. So you asked about OCR specifically. And so this is a very, I think, well-defined problem of converting, um, like an image to text. And so this is a very, I would say, well, I'm kind of changing my mind as I talk about how specific it would be to an application, right? So, I mean, if your application screenshots have a strange background that interferes with regular OCR algorithms, that could be a situation where, fine tuning is worth it. Um, but yeah, OCR, that's another thing about that is you probably need labels. So that strikes me more as a supervised fine-tuning task. So screenshots by themselves probably wouldn't be enough. Yeah, this is a great question as well. So, um, when should you fine tune versus providing additional context? So, I think there's a few ways to think about it, and one is based on you know basically if you think of it in terms of behavior or multi-step solutions, that's less likely to be represented in like context like a RAG that a RAG would provide. Um, so to give it more knowledge, yeah, the way I would think about it is that with context engineering, you can sort of just tell the model upfront, what you would have wanted it to learn. So, for example, the generalization or the pattern that you hope for it to learn, you could just state that if it's possible to state that. But training it to and actually scoring it and providing that numerical signal is going to allow it to have to store much deeper and richer reasoning, right? In its capability into the weights. Um, so yeah, that's a good question. I would say another like situation that's worth breaking down here is like if the model needs to have a very specific piece of knowledge, like the price of GPUs on Modal today, that is something that you shouldn't rely on training for it to have specific knowledge like that, unless it's allowed to go look stuff up on the internet. Which, yeah, in this case, I'm thinking about the RAG as kind of like a tool call to enhance the context. I think if there's time for like a couple more. Yeah, I think this is a really interesting question because this is part of what has changed. You know, so with supervised learning or self-supervised learning, designing a loss function numerically has been a pretty tough and highly technical problem. You need to understand the linear algebra and the mathematics and the calculus of the loss function you're designing and what effect it has. Um, it's kind of a broad statement. It's not always the case, but reward functions are very different because the gradient is not calculated, right? So the reward function doesn't even need to be uh, like a differentiable um, function. It could be, give it this reward if this happens, give it that reward if that happens. And so you can define reward functions at a much higher level. And this is what I was talking about around the question on what data needs to be collected. So you can provide rewards related to all the different steps of your agent's process, and not just the outcome, but give it some points for double checking its answer, or doing some other intermediate steps. Um, and this, yeah, not only is this intuitive, but it gives you a less sparse or a more dense reward. All right, I think I'm going to do one more. So modal containers can have up to 8 GPUs. And we do have a multi-node product if you need multiple containers, each with 8 GPUs. That's in private beta. So send an email to support@modal.com if you're interested in doing multi-node. And all right, yeah, I think that's it. So thanks everybody for joining today. It was a pleasure. And yeah, I'll see you at the next webinar.